Hello, my name is Craig Gallen. This is session 3 of the OpenNMS tutorials. And in this session, we're going to be looking at alarms and events. So session 3 can be found on Github, and we will have a number of exercises that we'll go through. But before we do that, let's just consider what alarms and events are within OpenNMS. If I go to the OpenNMS console and look at the event list, you can see that there are a number of events here. Some have come from traps, as you can see this one, but some have come simply from OpenNMS's internal operations. Node regain service would be as a result of a node coming up having been down for a period of time. Now at the moment, there are no alarms in the system, but I'm going to introduce an alarm by using MibBrowser. In this case, I'm going to introduce a link down alarm. So I send the trap, and if we go back to OpenNMS and refresh the screen, we can see now that minion 1 has got one alarm. And if I click on the alarm, we can see that the node here is minion 1. The log message is very simple: interface agent down, link down trap. And if I click on the number 5, the alarm number, we actually bring up the details of the alarm. The alarm has got an account of one event associated with it. And it has a log message and a description, which is a longer message than the log message. Log messages basically show up on the single line view of alarms and alarm list, whereas a description is much more detailed, along with other information that you might have in terms of operation instructions might be longer. An alarm also has this idea of a sticky memo and a journal memo. So a journal memo is a memo associated with this alarm. So I might want to tell somebody I'm dealing with this particular instance of this alarm, and I can save that information. You can see now it's updated with the date in which it was updated. But a sticky memo would basically tell a user that if this alarm ever happened again, then this is what you need to do. Now, if we save that, anytime this alarm occurs again on this device, then we will see this message. So journal memos are carried with the alarm, specific instance, whereas sticky memos are carried with the alarm type. If this alarm ever occurs, then you will escalate it or whatever you want to put in that. So those are alarms. Now, what's the relationship between alarms and events? Well, if we go to status and look at events, we can see under all events, we've got this single event, an SNMP link down event, and it's associated with the minion. Now, if I click on the event ID, you'll see that it has an associated alarm ID. And if I created a second event, then if I go back to the events list, you'll see that there are multiple events, all of which will be associated with the same alarm ID. And if I click on the alarm ID now, you'll see that there are several events associated with this alarm. So what's the difference between alarms and events? Well, an event is something has happened. It may be good, it may be bad, but it doesn't really tell you the state of the device. It just tells you something's happened. An alarm, on the other hand, is a state of the device. A device has got an alarm associated with it, and that alarm may have many traps, because usually when a device sends out traps for a situation in the device, it'll send out traps repeatedly after a period of time. So you may end up with a huge list of events associated with those traps, but you don't want to know about all those events. You just want to know that they are all associated with the same alarm. And that basically is the relationship between alarms and events. Alarms are a permanent state of a device, and they're controlled by events. Now, if I send in a link up alarm, in this case, I'll send that trap, we should see that this alarm clears. And if we go back to the alarm list, we'll see the alarm is cleared. And if we look at the events list again, we can see that we've got a normal event that's come in. So in this case, the link down event creates an alarm, and a normal event causes the alarm to go away. So a link up is determined to be a normal event. That clears the alarm. A link down creates an alarm. And if we go back again to look at our alarm list, we can see that the alarm is cleared. And actually, after a period of time, about 30 seconds or so, maybe slightly longer, the cleared alarm will actually be deleted from the list. So the alarm will no longer be there. So the first exercise we're going to look at is exercise 3.1. Now, I've already alluded to mid-browser, and I've also alluded to the project in which we're running this. So if I look at my session, you can see that I've got this minimal minion active MQ, and I've got a Docker Compose file in it. And as you can see, the Docker Compose file has got two networks. One network is on one side of a minion, the other network is on the other side of the minion. And the N000 network has got the OpenNMS database, OpenNMS Horizon running in it, and the minion also running in that network. But the minion is also able to see the N001 network. And NetSNMP is running on both sides. So we have NetSNMP 1.1 and 1.2, both running on the N000 network. And we have a Chubb camera, which we will come to in a bit. And then we have SNMP 2.1, 2.2, and then a second Chubb camera, both running on the other side of the minion. So that's our network. So what I'd like you to do as part of this exercise, first of all, you're expected, when you check out this code, to, instead of running directly in session 3, you will copy that into My Practice coursework and then run your example here. Because that way you can keep track of any changes you've made or any notes you might want to make. But it won't trip over any changes I might make to these sessions going forwards. So start off by getting your OpenNMS example up and running. The command for doing this is Docker Compose up. We'll look at mid-browser. Now the iReasoning mid-browser, I did set a link for this, but I'll just look it up now. Is currently running, and if I do a Docker PS, it's a very simple little tool. See, these are the services that are actually running all of my NetSNMP and my Chubb cameras, which basically allows you to. So that's the first thing you need to do. And in the same time, we will look at mid-browser. You can download it from iReasoning, install it on your machine, and I have an example of it running here. Now, if I just want to ask a device for its OID, then I can just put in a simple 1.3.6 and do a simple SNMP walk. And I'm actually stopping it before it completes because it's actually a very long walk and it'll go off the edge of the screen. So obviously the SNMP walk starts off with the system description. The Linux device has a system object ID, and you can see here the identifier for NetSNMP is 8072, and then various other bits of information about the device. And then after that, we have a load of MIB information which you OpenNMS can parse. And we're not going to look at all of that in detail at the moment, but I wanted you to understand that this was what you can do with MIB browser. You put in the address you want to go to and the port you want to go to. And in our example, if I look at our session 3 active MQ and look at the Docker Compose, again, you can see that if I go to the NetSNMP 1.1, it's port 11161. So we've started off, and in our trap sender, the first thing we've done is we've done a link up and a link down. Now, what I want to do is I want to send an SNMP v2 trap, and instead of sending a trap, that OpenNMS knows about, I want to send a trap that OpenNMS doesn't know about. In this case, I want to send a trap that is an unknown type. So I'm going to put in this particular OID. And I'm going to put in var, oh, sorry, excuse me, that's the OID there. Varbind 1 is an octet string. I'm going to post that in. Can be any text you want as a value. I'm going to add another one. In this case, it's not going to be an octet string. It's going to be an integer. And I'm going to put in integer 0. And then the final one is an integer 1. Okay, so I have a trap with a specific OID. I have various bits of information associated with that. The first varbind has got hello world. The second varbind is an integer with 0. The third varbind is an integer with value 1. Now, just to talk about a little bit this number here, the vendor identifier. Again, in the notes, you will see that there's a list of vendor identifiers which you can look at. Which will give you all of the enterprise numbers that are associated with each of these vendors. And you can see that there's a number list going all the way up. And in our case, when we were using OpenNMS and using NetSNMP, the number corresponded to NetSNMP. So you can look at the enterprise numbers, looking at the IANA. So if you want to know what vendor a trap has come from, this is the way to find out what vendor has sent that trap. Anyway, let's send our trap to OpenNMS. The trap's been sent. Let's go to our list of events. And you'll see that we now have an enterprise default event coming in. Now, all this event tells us is that a trap has been received by OpenNMS, but it doesn't have any configuration for it. And it drops down to the default configuration, which basically gives us some information on the event itself. What it tells us is that the first varbind had this particular value associated with it, and it was hello world. The second varbind at the value of 0, and the third varbind at a value of 1. And the mask elements are a way of telling OpenNMS how to create a mask for this alarm or event. So OpenNMS doesn't know what to do with this event, and it'll just give you this information. But having been given this information, you can actually then create your own event and alarm for this. We can also generate these events using NetSNMP. Now, I've shown you how to do it using MIB browser, but NetSNMP has got an SNMP trap command, and we can actually do the same thing using that SNMP trap command. So I'm going to use Docker Compose to get into one of the SNMP containers. And again, it's worthwhile following along and doing this yourself. I'm getting into that SNMP container as boot, as root, and now I can send that SNMP trap. I'll just send the same trap again. And if I go back to my OpenNMS and look at my events, you'll see that a new event has come in corresponding to the message that I've sent. And again, I can change that to correspond to the second event, where I'm going to send the final var bind as a 0. And again, if I send that view all events, we can see that the last var bind is now 0 instead of being 1. Okay, how do we decode this? Well, let's go back to our tutorial. And in exercise 3.2, we begin to think about event configuration. Now, I'm going to modify the event configuration through the UI. So we've covered this in a previous session, but I'm just going to very quickly do that. I've got to change the user permissions so that they can actually edit using the UI. And if I modify the admin user and I add in this file system editor and save this value, then now if I log out and then log back in, I can use the file editor. And the file editor will allow me to modify files that are in the etc. directory. Now, the file that I'm particularly interested in is the eventconf.xml. And you can see that the eventconf.xml references a number of other files, each associated with a different vendor. If I go back to my tutorial and look at the events folder, you can see all of these events are standard, pristine configurations that OpenNMS has. Let me just go and look at Cisco, for instance. You see there's a set of events defined for Cisco. And the key thing to understand is that for each of these event definitions, there's different text depending on what the MIB says about the information, and there's a different UEI, which is the unique vendor identifier for this particular trap translation. So all of the events for all of the vendors that OpenNMS knows about are held in the events folder, and the configuration file, which is the file eventconf.xml, references all of those events. Now, you can also put events directly in eventconf.xml rather than putting them in a separate file. And in this example, that's what we're going to do. We're going to put some simple events in this file. So let's go back to our tutorial, and we're on 3.2. And you will see that we are going to copy this set of events into our eventconf.xml file. They will go here basically after the global, but before all of the other files. I'll just put in a bit of space. I'm going to paste in these two event definitions, and I'm going to save that configuration. Now, what I've got to do now is I've got to reload the configuration. At the moment, the configuration file has changed, but OpenNMS is not aware of the change. So what we need to do is to send a command into OpenNMS that's actually going to change or reload that event daemon. Now, on OpenNMS systems that are installed on a standard Linux distribution, direct install on a virtual machine, for instance, then that distribution will almost certainly have Perl. And so this command here, sendEvent.pl, which is in the bin directory of OpenNMS, will run up the OpenNMS quite happily. However, in our container, we don't have that luxury. We don't have the ability to run that Perl command. So what we can do is we can either send a post into the REST API of OpenNMS, or we can run a command in the SSH console for OpenNMS. But either way, what we're doing is we're sending a command to reload the daemon, and the daemon we want to reload is event-d. So I'm going to just use this curl localhost command, which again is just posting an event into OpenNMS with the daemon name and event-d. So let me get into OpenNMS first of all. Oh, sorry, Horizon. So docker compose exec horizon bash, and then I can use that curl command. And I've just posted that event into OpenNMS. And if I go back to the OpenNMS web console and list events, just view all events again, you can see that we've had this reload daemon config event, which loads the event-d configuration file, and the changes were applied successfully. So we're now able to use that event configuration to receive events. So let me send those traps again. And if you remember, the first trap that I sent had a value of 1 for this final var bind. And I'm going to send that event into OpenNMS, view all events. And you'll see that now we have a trap definition for a raise. And this is of a warning type, and it's raising an alarm. And these are the var binds associated with it. Okay. Now, this is an associated alarm. So again, if I look at the alarms page, you can see we now have an alarm, and we can see that this alarm definition corresponds to that raising trap. Now, if I send the other trap, which was the clear trap, we will now see that the alarm is cleared. If I just refresh this. And you can see the events associated with this trap. Here, we've got the raise and we've got the clear. And if we click on this, we'll see the event associated with the clear. Okay, now that change in behavior has come from the changes that we have put into OpenNMS. So let's look at the changes that we have actually made to OpenNMS itself. And this is the file that we changed. And you can see that there are two mask elements. This first event definition, we have the mask element, which we would have got from that unformatted enterprise event. But we also have a var bind definition. And in this case, if the third var bind is a value 1, then we're going to call this a raise alarm, and we create a UEI that is unique. Now, the UEI is a unique event identifier, and every event definition in OpenNMS has to be unique. So in this case, we are creating an event definition, and we're calling it an example definition raise. Now, the important thing to understand is that var binds in OpenNMS are only really read in terms of their position. We don't care that the var bind may have an OID associated with it. So if you look at the trap that we sent, you can see the trap itself has, this is the first OID, which is the OID of the trap. But then each var bind also has an OID of the var bind. In this case, 1.3.6.1.4.1.2523330, 0.6.2, 0.7.0, and it's a string, S, and then the string is XXXX. And I'm not going to read out the others, but you can see that the second var bind is 0 and the third var bind is also 0. And we've defined, we've got it possibly from the MIB, that the third var bind is what we care about, and the third var bind, if it's value 1, then it's a raise, and we can see far down here that if third var bind is value 0, then it's a clear. And we've created an event raise definition and a clear definition. The raise definition has got severity of warning. The clear definition has a severity of normal. The other thing to note about the events is that we have these parameters, parameter 1 and parameter 2. These parameters actually also corresponds to the var binds. So var bind 1, var bind 3, which we care about, is parameter 3. But we can also pull up the other var binds, even though we're not using them in the event definition itself. We can use them in the text. So the text of the event, we can use a parameter directly to show us what the text is. And you'll see again, if you look at the events, that clearly, example trap definition 1, clear var bind 1 is XXX, var bind 2 is 0, var bind 3 is 0. Those have been substituted in that event definition here. Now, what about the reduction key? Well, the reduction key is a way in which OpenNMS keeps track of all of the events that come into the system and turns them into alarms. And an alarm type 1 is a definition that will generate an alarm raise. And in this case, the UEI is essentially the UEI here, the actual UEI of the event itself. The DP name tends not to be used, but it's the distributor polar name, which again may be unique within OpenNMS, but as often this has got no value associated with it. But the important one here is the node ID, is that if we get an event which has this UEI with this node ID, the first time we get the event, we create an alarm. But if we get the same event again, then we just add to the count of events in the alarm, but we don't create a new alarm. So this is what deduplicates the events into a single alarm. Okay, so that's how we raise alarms, and that's how we count the traps. What do we do when we want to clear an alarm? Well, in this case, we have, again, an event that we've defined, but in this case, because of var bind is 0, we're going to create a UEI of clear trap definition. And the important thing to see is that it still has a reduction key. So if we had multiple clear events came in, we'll only have one clear alarm because the reduction key is going to reduce those clear events down to a single alarm. But in this case, it's alarm type 2, and that tells us that we need to clear an alarm that already exists. How do we know what alarm we need to clear? Well, we look for the clear key, and the clear key is going to match the reduction key of the alarm that we're clearing. So our alarm that we want to clear is this trap definition raise. The reduction key UEI DP name node ID. You can see here we're matching this UEI trap definition raise, but we're also matching the node ID, and therefore whenever a clear comes in, it's going to clear an event that has that raise definition associated with it. So that's how we clear and raise events. Now, while we're here, the only other thing I want to point out is this auto clean equals false. Now the alarm is cleared, so I need to send that trap again, so we are going to raise that alarm. And we can see the alarm's raised, and we have a count of 1. And we send it several times. You can see the count is 4. And if we look at the alarm, you can see all of these related events are associated with it. Now, if this auto clean was set to true, then whenever we go to the alarm detail, only the last event would be stored. The other events associated with this alarm would have been deleted. And that allows us to reduce the amount of events that are stored in our database. If we've got thousands of traps coming in, we actually don't want thousands of traps associated with one alarm. We can get rid of all the other traps that have come in and just save the last one. And that's what that would do. But in this case, we're just going to have the events that come in. We're not going to clear them. We'll only deal with them once the alarm has disappeared completely. So that's the alarm raise and the alarm clear. And you can see that we're able to count the events as well that come in. Final thing just to talk about is this log and display. It's also possible to put in here, do not log, do not display. Look at the documentation, you'll see the options. But at the moment, this log message is logged in the database and it's displayed for the user. We could set it to just log it in the database and not display it to the user. And we could also set it to do not log, do not display, in which case the event will be created on the event bus, but will never be put into the database. Other daemons that are listening for that event will hear the event and act on it, but the event itself will not be persisted. And we'll see when we look at the event translator in a following session that the event translator, whenever you pass an event to the event translator, you may want to make that an event that is not logged, because the event translator will actually translate that event into an event you do want to log. And that way it'd be easier to see what's going on when you've translated the event. I should finally point out that in the tutorial I talk about some properties which are available for the OpenNMS alarm daemon. The first property is new if cleared alarm exists. Normally when an alarm is cleared, then eventually the alarm will be deleted. But if an event comes in that will cause the alarm to raise and the alarm is not cleared, then the default behavior of OpenNMS is just to change the state of that alarm back to its uncleared state and put the severity of the event against the alarm. Now, that's a perfectly reasonable behavior, but there are use cases where you actually want to create a new alarm every time this happens. So whenever an alarm clears, that alarm is cleared, it's closed, it's done with, and if after that a new event comes in which would raise that alarm, the cleared alarm is left alone, eventually to be deleted, but a new alarm is created. Now, the reason why that might be useful is that often you want to know the beginning and the end of a problem. And if you've got unique alarms which have beginning and end associated with them because you raise it and then you clear it, that can help you calculate your SLA. But the other side of the coin is if it's a flapping alarm that comes and goes all the time, you could end up with lots of alarms cleared in your alarm list and you may not want that. So this allows you the option to just clear an alarm or just keep the cleared alarm and change it back into its old state. The other interesting thing is the alarm list page options, where we can generate a sound based on the changing of an alarm, and we can also make the alarm flash rather than have a separate acknowledged and unacknowledged state for alarms. So if we look again at our alarm web console, you can see at the moment that alarms are either acknowledged or not acknowledged. If I go to unacknowledged alarms, there aren't any. And if I look at acknowledged alarms, then we'll see there's an acknowledged alarm. Now, if I acknowledge that alarm, it disappears from the list. But if I change the filter, I'll see that this is an acknowledged alarm. Now, that's a fine behavior if that's the behavior you want. But quite often, what you actually have is several people looking at the alarm list at the same time. And what they'll want to see is that alarms are acknowledged or unacknowledged on the same list. And by making unacknowledged alarms flash, that means that a user can say, oh, there's a new alarm that I need to look at. They'll look at it, they'll acknowledge it, and then it will still stay on the list, visible to other people, but it won't be flashing. And that might be a more useful behavior in certain operational scenarios. So you can see in my example here, I have set the cleared if new alarm exists equals to true. And I've also changed the alarm page so that where sound is enabled and unic flash is true. So if I go to my alarm page, you can see there's no alarms on it at the moment. And if I send a trap, you can hear the little sound, and you can see that there's a warning, and it's flashing because it's not been acknowledged. And if I acknowledge that alarm, you see it's no longer flashing, but the alarm list will have both unacknowledged and acknowledged alarms on it at the same time. So, in summary, we've talked about using event definitions, and we've talked about how we can create raise alarms and clear alarms. We're now going to look at a more complex example. Now, in this case study, we're looking at Chubb cameras which are used in the United Kingdom on smart motorways. And Chubb publish a MIB for their cameras. And we can actually look at that MIB if we load it into the MIB browser. So to do that, in the MIB browser, if you've got the MIB checked out, you can load the MIBs and pick the file that you want to look at. You're going to have to look at the Chubb route and the TVS camera together. You open those and you can actually go down then and look in the MIB browser at the MIBs associated with the device. Now, there's some notifications we're interested in. There are 6 types of traps: health change reason, tamper state, logic input state, fault state, common state reason. Now, the only thing we're really interested in for this example is the health change reason, for which you can see there are a lot of values for each of the devices that can have a problem. So this same trap is used for multiple different alarms. You can see the tilt motor can have an alarm, the zoom motor can have an alarm, the focus motor can have an alarm, etc. And you can see that, depending on what the health change reason is, that will give us which device we've got and what's going on. Okay, so that's the trap. Now, these are the definitions. Now, the traps themselves, you can see, have their own definition. Each of these events will have its own set of values associated with it. And again, there's only some of the traps we're interested in. So that's how you would go about browsing the MIB itself. What we're going to do is actually import that MIB into OpenNMS. But before we do that, let's get started with actually getting the project up and running. So as before, we go to the minimum active AMQ. Now, we want to delete the previous database. So use docker compose down -v first, and then docker compose up -d, which will allow you to see a new database in OpenNMS, and it will take a while for it to start up, so just leave it running. And what we'll see is that there are 2 camera definitions in this example, camera 1, camera 2, which are simulations of the camera. We're using a project called SNMP Sim to simulate the camera. I'm not going to go into that in any detail, but the fact is we've taken a walk of the camera and used that to simulate the actual device. What we can actually do is we can log into the camera itself. So we'll use this command. And on our running example, we will go docker compose exec chum camera bash, which will get us into the camera, and then we can do an SNMP walk within that camera to see what's going on. And you can see there's not an awful lot of information there, but it does tell us the OID of the camera and a little bit of information about where the camera is, which has been set by the installer. So that's proving that the camera works. And look at the provisioning requisitions associated with this example. Now, this is the requisition we want to load. We'll just look at it. It's all the stuff we looked at previously with Net and SNP, but we've got these 2 Chubb cameras which we care about now. So we're going to synchronize this, pull in all the nodes, and we will also need to set up OpenNMS so that it can have the right community strings for that camera. In my SNMP configuration, I'm going to look up that camera, and we'll see that it's set to public. We need to set that to Chubb. Save the config. So we set up the Chubb camera. Now, what we need to do is to load the SNMP MIB for this camera. And to do that, we go to the SNMP MIB compiler. And we need to upload the MIB and its dependencies. So let's upload the MIB. And if we just upload the Chubb TVBS camera MIB and open that up, if we try to compile that, it'll fail. And the reason it will fail is because there are these dependencies in the MIB that have not been loaded. So I need to load these. So I'm going to upload all of the dependencies. And you can see I've now compiled them all, but I had to compile a number of dependencies for it to work. So now we're in a position, having compiled the MIBs, to actually take them and create events from them. So let's go to generate events. Now you can see that there's a generate data collection as well. We'll cover that later. But for now, we're just going to generate events. And you can see that you can choose the UEI that you're going to use as a base, but this is perfectly sensible UEI, Chubb TBBS camera MIB. I'm just going to continue with that as the base. And you can see that this particular MIB has got 4 events defined, and I'm just going to save the events file. And you'll see at the bottom here that eventconf.xml has been saved, and the Chubb TVBS camera MIB events.xml have also been saved inside the system. Under the info, we can now look at the file editor. And if we look at the event.conf file, we can see that actually it now contains a link to this Chubb TVBS camera MIB events. And we can look in the events folder and see that the actual definitions are held in the events folder. So OpenNMS has actually got the ability to see these events now. They're not perfect yet. We'll need to rework these events, but for now it's got them. Now, in reality, this is events that are stored in OpenNMS. You're going to have to copy these files outside of OpenNMS to edit them, and then copy them back in. You don't want to edit them here because remember, the OpenNMS is running within a container. Reload config has happened. We now need to send an event to OpenNMS. This command, which is an UPA command. We can see we've now got a definition for this, but it doesn't really tell us very much. It's an indeterminate alarm, and we don't know if it's clear or raise. If I send another event to OpenNMS, this time value 0, and we go back to the events, you see there's now 2 events, one with a clear, one with a clear. Different reasons associated with them. Really doesn't mean an awful lot. But at least we're pulling in the health change data, and we've got some part of the definition for this alarm in place. So having created the eventconf.xml and the Chubb TVBS camera, we can now copy these out of the container in order to modify them. So if I take this particular command here, and run that copy, you can see that the file has been copied into the local container. And now I can edit it and do something with it. Now, we're going to go on and look at how we will edit that file, but in order to do that, I've actually pre-created some files that we can actually do something with. So if we actually go to our example configurations, you'll see that there are several different ones. The first example configuration is just the one that we've copied out. It's basically the raw, unchanged events that were generated from the MIB. I'm not going to look at those because we've already seen them in the event browser. But then we've got simple alarms from the MIB,
And then we've got fully decoded set of alarms from the MIB. So let's look at these and see what they would look like. So what we'll do is we're actually going to copy this example into the OpenNMS so that we can actually use that now going forwards. So I'm going to copy that file into the etc. directory. And I'm also going to do the same with the other command. Copying that new TVBS camera MIB into the directory. In this case, we can just do a simple reload command to load it. Using docker compose exec. This time I'm doing it from within just the main project and not actually logging in directly to the system, but it actually works. Now you can hear the wee noise happening, and that's because I've turned on the alarm noises. So if I view all events, we'll see that we've got a health change raise that's happened. And I'm actually going to click on that alarm. And you can see that I've got information here about the alarm. Health change not received. Pan motor is the reason, and the change to 1. That's good. And if I go to alarms, see both alarms are flashing because they haven't been acknowledged, but I'm going to click on that, and we can see that now we have the health change raise. And we've used the parameter to actually determine which raise we're actually going for. So the parameter here is used for that. Okay, so this is a health change raise, and in this case, we've specified that it's a pan motor that's a problem, and the fault state is triggered. And if we send a clear alarm, we refresh this, we should see that the alarm is now cleared. Okay, so how does this alarm definition work, which is under the examples? We're looking at the simple set of alarms from the MIB. And if we have a look at how it's defined, you can see that I have health change alarm events, and I have a raise event, and I have a clear event. You can see the clear event's normal, and the raise event is not normal, it's warning. Now, all of this information in the MIB, or the description, has come from the MIB. All of that information has come. So the description and the log message I haven't written, that's been generated directly from the MIB. But very cleverly, the system also is able to decode each of these varbind values. So the varbind value 0 to 12 is decoded into these strings: pan motor, tilt motor, zoom motor. So if we include those strings, parameter 1, for instance, in our text, then it won't be the parameter 1 that's put there, it'll be the actual string that's changed. The health change reason is shown up as parameter 1. And if I go to the alarm, you can see the health change reason in this case is showing up as pan motor 1, and health change reason here is pan motor as well. So that text has actually come from that definition. Okay, again, you can see in the OpenNMS version, same thing. So that defines what the text comes from. But the other thing that we've done that's clever is we've included parameter 1 in the alarm UEI. So that means because that parameter 1 can have any one of these values, we can create up to 12 different types of alarm using that same trap. Now the disadvantage of doing it this way is that the severity warning will be applied to all of these. So it may be that some of these are more important than others, but they're all still going to get the same severity as warning, which obviously is not as good as if you had different severities for each example. So, but we can just define two traps, a raise and a clear, and you can see the clear and the raise are very similar. But in this case, again, we've included parameter 1 at the end of the clear key. And that means that in both cases, these traps will do two trap definitions will define all 12 alarms, because we're not explicitly defining the values in the trap definition. We're just using OpenNMS to use that var bind number as part of the reduction key. So that's the simple alarms. Now, I'm not going to go through this in great detail, but you can actually define a fully decoded set of alarms. So instead of just having the two alarms, you can actually, as we can see in the fully decoded set, we've got pan motor change, in which case we're using var bind number 1 of value 0 to tell us it's the pan motor. And we go down, we can see that there's other examples here. Tilt motor change, in this case it's var bind number 1 value 1. And then value 2 will be, the zoom motor and then the aperture motor. So we're using two var binds here. One to give us a state, so it's either a bad state or a good state. And then the var bind itself, number 1, is telling us which of these alarms. So in this case, it's a much, much bigger file because I've defined alarms for every possible state of whether it's pan motor, tilt motor, or whatever. But it's fully decoded. Now, you could mix and match. You could just have one or two fully decoded examples. But in that case, you must make sure that the non-fully decoded examples, examples from the simple example, go after this. So you could have, say, for instance, we wanted this to have a unique severity. Pan motor is, it's much more important than anything else. So we make that a critical alarm. We could put this in, and then we could go back to our simple alarms. And then after that definition of the specific alarm, we would just put in this less specific example that just carries all the rest. But remember that the order in which these are processed is determined by the order in the file. So these simpler definitions of alarm change events would have to go after the specific definition of the events that you'd use from the other example. So I hope that gives you a good example of how you can parse a real MIB for smart motorways and generate multiple alarms for that camera depending on the different states of the pan motor and other things in the camera. We will, in the next case study, look a bit more at this example using the event translator.